Okay, let's dive right into this explainer and uncover the hidden plumbing of the internet. Have you ever actually stopped to think about what happens the exact millisecond you type a website name into your browser and hit enter? I mean, it feels totally instantaneous to us, right? But underneath that split-second load time is this incredibly complex, globally coordinated journey. Today, we're going to trace that exact journey from start to finish.
So think about the sheer, unfathomable scale of the internet for a second. We're talking billions of devices, millions of miles of fiber optic cables crisscrossing the oceans. When you want to visit a site, like let's say you're literally trying to figure out how Google finds websites, how does your specific smartphone know exactly where to send your data across the globe? And on the flip side, how does Google know exactly how to route its search results right back to your device? Honestly, it's a modern miracle of engineering.
Here's our roadmap for this explainer. We'll quickly run through 1. Mapping the digital world, 2. The IP address shortage, 3. Subnetting dividing the network, 4. IPv6, the infinite upgrade, 5. Routing, directing the traffic, and wrap up with 6. Firewalls, securing the perimeter.
All right, let's kick things off with Section 1, Mapping the Digital World.
The absolute foundation of how Google finds websites and how we find Google is DNS, or the Domain Name System. You see, computers don't understand words at all. They operate using logical 32-bit IP addresses. But humans, we are notoriously terrible at memorizing random strings of numbers. DNS is what bridges that gap. It acts exactly like the internet's literal phone book. When you type in a human-readable host name, like google.com, DNS dynamically maps that name to the specific IP address the machines actually use to locate each other. It's the ultimate translator between human memory and machine logic.
Moving right along to Section 2, the IP address shortage.
Now here's where things get really interesting. When the internet just absolutely exploded in popularity, we realized pretty quickly that we were running out of those 32-bit IP addresses that DNS was busy handing out. To see why, you got to understand how an IP address is built. Every IP address is split into two parts, a network identifier and a host identifier. Think of it just like the postal service. The network identifier is your street name. It gets the data to your general neighborhood. The host identifier is your exact house number. It delivers the data right to your specific device. And the invisible line dividing those two, that's what we call a subnet mask.
Back in the early days, the internet used this rigid, classful network system. You were assigned either a class A, B, or C network. But man, was this wasteful. Imagine a company that only needed 2 IP addresses for a simple connection between 2 routers. Under this old system, the smallest block they could possibly get was a class C network, which gave them 256 addresses. So they used 2 and literally wasted 254. You can see why this just wasn't sustainable for very long.
Which brings us to Section 3, Subnetting, dividing the network.
So, if we were rapidly running out of addresses because of these clunky classes, how on earth did the internet survive? Well, the heroes here were CIDR, classless inter-domain routing, and variable length subnet masking. Basically, CIDR threw those old class A, B, and C rules completely out the window. It let network engineers assign IP blocks of any size using what's called slash notation, like a /24 or a /26. This meant engineers could custom zone their digital neighborhoods. If you only need 2 addresses, boom, you create a tiny subnet just for that. It saved a massive amount of IP addresses and seriously cut down on unnecessary network traffic.
Now, I know figuring out the binary math behind these subnets can sound super intimidating, but let me show you this brilliant shortcut called the magic number hack. Forget the complex binary for a second. You just take the last number of your subnet mask. Let's say we have a /26, so that ends in 192. You just subtract that from 256. 256 minus 192 is 64. That 64 is your magic number. To find your subnets, you literally just count up by 64. So your first network is at 0, the next is at 64, the next at 128. It is seriously that easy.
Now the real kicker here, the crucial thing to remember, is that when we calculate the actual usable hosts inside one of these subnets, we always have to subtract 2. Why? Because every single subnet automatically loses one address right at the start to identify the network itself, and one address at the very end to act as the broadcast address, which is used to shout out to every host on that specific subnet. You never get to assign those 2.
All right, Section 4, IPv6, the infinite upgrade.
So subnetting and CIDR were a fantastic band-aid. They literally kept the internet running for decades. But they weren't a permanent cure. Right now, we're transitioning to the ultimate fix, which is IPv6. Just look at the contrast in scale here. IPv4 uses 32 bits, leaving us fighting over a scarce pool of about 4.3 billion addresses. But IPv6, it uses 128 bits. That gives us 340 undecillion addresses. It's an almost incomprehensibly large, virtually unlimited address space.
And just to wrap our heads around how massive 340 undecillion actually is, if all 8 billion people currently alive on Earth had 1 billion separate internet devices each, IPv6 could still accommodate that entire massive global network 42 billion times over. Let that sink in. Literally every tiny device on the planet can have its very own public address.
Let's shift gears to Section 5, Routing, Directing the Traffic. So our naming system is working, and our IP addresses are perfectly zoned into subnets. But how does the data actually travel from point A to point B? Routing basically comes in two flavors, static and dynamic. A static route is exactly what it sounds like, literally typed in by a network admin. It's fine for a small test lab, but if a cable gets cut, the whole route breaks. Dynamic routing, on the other hand, uses protocols like OSPF. These routers are constantly talking to their neighbors. They automatically learn the network map and adjust their routes on the fly when traffic spikes or equipment goes down.
In the real world, it looks a lot like this. A router sits right there in the middle of those perfectly sized subnets we just calculated. It's the gateway. So when your laptop on a local network wants to talk to a server out on the internet, the router reads that destination IP, checks its dynamic routing table, and actively directs that packet out to the wide area network to find its way. And finally, we hit Section 6, Firewalls, Securing the Perimeter.
Okay, we've built the roads, assigned the addresses, and routed the traffic. But now we gotta secure the perimeter to keep the bad guys out. According to NIST, a real security perimeter isn't just one giant brick wall. It's a layered defense-in-depth strategy. You've got the hardware layer locking down Ethernet, the network layer inspecting IP packets. You have HTTP proxies filtering web pages, and you've got web application firewalls, or WAFs, hunting for malicious API traffic. It's basically a series of highly specialized security checkpoints.
But in our current IPv4 world, the real MVP of network security is NAT, Network Address Translation. Since public IPv4 addresses are so incredibly rare, companies use private IP addresses internally. NAT acts just like a corporate receptionist. It takes requests from thousands of private internal devices and routes them all out to the internet using just one public IP address. It effectively hides your entire internal network structure from the wild west of the outside world.
But here's a wild thought for you as we look ahead. If IPv6 is going to give every single device on Earth its own unique public address, that completely eliminates the need for NAT. So how is our approach to firewalls and network perimeters going to evolve next? I mean, if there's no NAT receptionist to hide behind, security has to drastically adapt, right? It's a massive shift in how we build the digital world, and definitely something to keep your eye on. Thanks so much for joining me on this explainer of the Internet's hidden plumbing.